Okay, so this is the last little section that I want to spend some time reviewing before we send you off to the adventures of calculus. Um, this does come up. This is a big concern. I see a lot of students in calculus kind of get nervous about their trig skills. So the intention is, let me show you the type of calculus level question that you would actually encounter that involves trig in it. Um, just remind you of a couple different types of things that could come up when you're solving trig equations. You could see what's called a linear type equation, and the way we know it's a linear type equation is it's a single trig statement that I can easily manipulate and get it to look like one side of, or get it on one side of the equal sign. So something like 2 sine x minus 1 equals 0. It has only one trig statement in it, and so I can isolate it out. So if I add 1, I get 2 sine x equals 1, sine x equals a half. Okay, and I guess I should say for the domain and all this, and if I don't say this, are going to be from 0 to 2 pi. I think I did in the practice, but I don't think I said so in this in the notes example. Okay, so what I'm looking for here, if I look at the unit circle, where in the unit circle do I find a sine value of 1/2? Well, I know it's positive in the first, and I know it's positive in the second. So there's got to be an angle that has that corresponding sine value, and that would be, let's see, x equals pi 6 and 5 pi 6. Okay, and you're going to see a lot of these little sketches of the unit circle where I'm just trying to remind myself of all the various places that I want to find for my solutions. Okay, factoring. Okay, factoring examples typically have, and I say typically because there's going to be counterexamples, and I'm sure they're out there. Factoring examples typically have two trig statements of the same variety, so two sine statements or two cosine statements, but one statement is squared, and the other is not squared. Something to, okay, so an illustration of this would be 2 sine squared x plus sine x minus 1 equals 0. Okay, and we're going to factor this thinking that sine is a variable. So if I factor it out, I get 2 sine x and sine x, and then I have to have a 1 at the end, and it's just a matter of balancing out the signs. So it's going to have a positive, the bigger thing is going to be positive, so 2 sine x times 1, because that's got to be positive, and that piece has to be negative. And then I can take each of these things, these binomials, set it equal to 0 and solve. And sine x plus 1 equals 0. Okay, so this will eventually give me sine x equals 1/2, and this will give me sine x equals -1. Okay, so remind myself again, we just did this one, but sine is positive in the first and the second, so that would give me pi 6 and 5 pi 6. And sine is -1, so if I think about where that is, that's got to be down there. And that would mean 3 pi over 2 would also be a solution. Okay. Half angle. Going to sound really obvious when I write this. Half angles involve theta over 2's. That's how you know you're dealing with a half. But let me kind of remind you here. If in a typical domain statement, typically theta goes from 0 to 2 pi, well, pi halves would only go from 0 to pi. So because we're solving for theta over 2, we wouldn't have to look for all, where is sine positive. We wouldn't look at all four quadrants. We'd only have to look at two quadrants. So that does kind of save us a little bit of time. And that's half of the story. There's kind of more to it than this. But let me kind of pull up an example of this. So I get sine of theta over 2 equals square root of 3 over 2. Okay. This one's pretty straightforward. I want to figure out where sine is positive, and I'm only looking at things in the first and up to pi. So it's positive in the first and the second. So in this case, we actually do get two answers. And the first one, so I get theta over 2 equals pi thirds. And the second one, I get theta over 2 equals 2 pi thirds. Okay. So that's theta over 2, though. I want to solve for theta. So theta would be, I'm going to multiply both sides by 2. Theta would be 2 pi thirds, or 4 pi thirds. Okay. Now, just a subtle comment, it's okay for theta to be outside of that 0 to pi range, because we're focusing our efforts on theta over 2, but in the end, we do want theta. And theta can live between 0 and 2 pi. So it's okay to have two values that show up for that. Okay. All right, so lastly, let me talk about multiple angles. That does come up. So multiple angles would have something of some multiple of theta, where that something is not 1. Sounds silly to say that. But let me point out, say we're looking at 2 theta. Well, if normally theta goes from 0 to 2 pi, okay, 2 theta would go from 0 to 4 pi. Okay, all that really means is we're going to go more times around the unit circle than we thought we would have. So, let me give you an example of this. Say theta is tangent of 2 theta equals square root 3 over 3. Okay, where do I find tangent being positive? I find a positive tangent in the first and in the third. Okay, and so 2 theta would be, in the first quadrant, that would be pi 6. And then in the third quadrant, that would be 7 pi 6. Okay. But remember, we're dealing with 2 theta here, so I'm going to go around the unit circle one extra time. So if I add 2 pi to pi 6th and 7 pi 6th, so I get 2 theta equals, pi 6 plus 2 pi would be 13 pi over 6. And 7 pi 6 plus 2 pi would give us 19 pi over 6. Okay. And one more reminder. So let me just kind of point this out. So in case you didn't catch me say it, I did pi 6 plus 2 pi. And I did 7 pi 6 plus 2 pi. And I did that because of the 2 theta. Okay. Now in each of these 4 little mini equations, I've got them all set up for 2 theta. I still want theta. So in each case, I'm going to divide by 2. And that'll give me pi twelfths, 7 pi twelfths, 13 pi twelfths, and 19 pi. Sorry, let me try that again. 19 pi twelfths would be our 4 answers. Okay, so now that we've talked about the general types, let's just dig in and try to work some examples. So in number 1, it looks like a linear type, so there's a single sine function that I can get by itself pretty easily. So if I say 2 sine theta, if I subtract off the 3 from the 2, I get negative 1. And then divide that by 2, so I get sine theta equals negative a half. Okay, so looking at the unit circle, Where do I see negative sine values? I see them in the third and in the fourth. And then what angle corresponds to that? That would be 7 pi sixth and 11 pi sixth. Okay. Number two. Okay, I got a singular trig function. Oh, there's a squared there, so it doesn't quite fit the factoring example. I'm going to bring the 1 over, so 2 sine squared theta equals 1. Divide by 2 equals 1/2. And then when I square root that, I get sine theta equals, remember if you square root, you should get plus or minus square root of 1 over 2, which when we rationalize that, we get something we should recognize, which is square root 2 over 2. Okay, well, looking at the unit circle, where do I see positive and negative square root 2 over 2's? I actually see it positive I get in the first and the second, and the negative I get in the third and the fourth. And so these are all the 4 forms of pi force. So theta would be pi force 3 pi force, 5 pi force, and 7 pi force would be all 4 of our answers. Okay, so in number 3, we're looking at tangent of 2 theta equals -1, and we're looking at a multiple angle problem. So that means we're going to go around the unit circle twice to get our answer. And just a quick reminder, where do I even see a negative tangent to begin with? Tangent is negative in the second and in the fourth. So when I go collect up all my answers, if I'm in the second and it's got a -1 tangent, that means I'm looking at 3 pi force. And if it's in the fourth and it's negative, and it's got to be 7 pi force. Okay, and that's just the first round of this. So I'm going to take 3 pi force and I'm going to add 2 pi. So I'm going to write it as 8 pi force just so I can get common denominators. And then I'm going to take 7 pi force and I'm going to add again 2 pi, which is 8 pi force. And so the next set of angles I pick up would be 11 pi force and 2 theta would equal 15 pi force. Okay, now these are all 2 thetas. I want thetas. So I'm going to take every one of my fractions and I'm going to divide it by an extra 2. So 3 pi force divided by 2 is 3 pi eighths. 7 pi force is 7 pi eighths when I divide that by 2. Then I get 11 pi eighths and 15 pi eighths. And I just realized I did not include the pi when I wrote that. Okay. All right. Number 4 is a slight variation on that. I'm going to modify the question just in case we're not quite up on our cotangent facts, because I can rewrite this as tangent using a reciprocal identity. So tangent of 2 theta would be -1 over square root 3. Okay, but that really is just negative square root 3 over 3. So if you didn't recognize, oh, what do I do with the negative square root 3? Hopefully now we do. And either way, where do I see a negative tangent? That's in the second and in the fourth. Okay, but keep in mind we're looking at 2 pi thirds. So if normally theta lives between 0 and 2 pi, okay, where does 2 pi thirds, sorry, 2 thirds theta would be less than 4 pi thirds. Okay, so my next follow-up question is, can I be in the fourth quadrant if the biggest I can get is 4 pi thirds? And the answer is no. So I only have to worry about the second quadrant answer for this particular problem. Okay, so 2/3 theta is going to equal, well, what angle in the second quadrant has a tangent value of negative square root 3 over 3, or cotangent value of negative square root of 3, and that would be 5 pi sixths. Okay, so then I want, still trying to solve for theta. Okay, so I want, let's see, I'm going to divide by 2 and multiply by 3, so 3 halves times 5 pi 6, which gives us 5 pi over 4, would be that one. Oops, too far. Okay. Number 5, we're looking at sine squared equals sine x. This fits under the factoring umbrella. So when I bring all of the signs to one side, so I get sine squared x minus sine x equals 0. Okay, then I'm going to factor out a sine. So sine x, and that would be sine x minus 1 equals 0. And then I'm going to set each of those equal to 0. So that's sine x equals 0. And this would be sine x minus 1 equals 0. So that's going to give me, well, sine x minus 1 equals 0. So that'll give me sine x equals 1. Okay. Well, where do I see sine actually equal to 0? I see it equal to 0 on the x-axis at 0 and at pi. So let me write this out, that x is 0 and pi. And then where do I see a sine value of 1? That's up at the top there at pi halves. Okay, same number 6, exact same skill. We're in factoring mode, so I've got more than one statement. So I'm going to bring the tangents together. So 3 tangent cubed x minus tangent x equals 0. Then I'm going to factor out a tangent, so tangent x, so that's 3 tangent squared x minus 1 equals 0. So already I get tangent x equals 0. And then this thing I get, let's see, tangent squared x would be positive a third. So if I take the square root of that, I should get tangent x equals plus or minus square root 3 over 3. Okay, so let's talk about where is tangent 0. Tangent is 0 where the y value happens to be 0, and that's at 0. So let me write this out here. That's at 0 radians and pi radians. Okay. Where do I get plus or minus tangents of square root 3 over 3? Well, that's in the first, second, third, and fourth. So it's all forms of pi 6. So pi 6, 5 pi 6, 7 pi 6, and 11 pi, 6. My 11 and pi looks pretty much the same. 11 pi 6. All right, it'd be a shame if we didn't work in some identities into this process. So here's a nice typical one you might encounter. I've got a mixture of sines and cosines. Now, I won't worry with double angle, half angle, or fun things like that. One thing you do know how to do, and you'll see it more in Cal 2 than you'll see in Cal 1, is know how to convert sines into cosines or cosines into sines. Okay. So I'm going to take the sine squared, and I'm going to use the Pythagorean identity and swap it out with 1 minus cosine squared. And then minus cosine squared equals 1 plus cosine. Okay. And then this thing is just screaming quadratic format to me. So if I combine like terms, I should see 1 minus 2 cosine squared theta equals 1 plus cosine theta. Okay. And hopefully you notice, hey, the ones cancel each other out. If I bring the ones together, that means there's no more ones. But so I do want to bring all the cosines to one side. So 0 equals 2 cosine squared theta plus cosine theta. And then I'm going to factor out the cosine. So 2 cosine theta plus 1. Okay. And then set each of those things equal to 0 and solve. So cosine theta equals 0. And this would be 2 cosine theta plus 1 equals 0. Or cosine theta equals negative a half. Okay. So where do I see a positive, where do I see cosine of 0? Well, cosine is 0 at 0 and pi. And then where do I see cosine being negative a half? Well, cosine's negative in the second and in the third. And so the unit circle angle that correlates to that would be 2 pi thirds and 4 pi thirds. So that's that one. Okay. Number 8, kind of a variation of the same process. This time I'm going to take the cosine squared and convert it to sine squared. So 1 plus 2 sine theta, 1 minus sine squared theta, and distribute that in. So 1 plus sine theta equals 2 minus 2 sine squared. And I'm going to bring everything to the same side. I'm a big fan of positive squared things if I can make it happen. So I'm going to bring everything over to the left. So that's 2 sine squared theta plus sine theta. And that would actually be minus 1. If you bring the 2 over, then it's a minus 2, and then plus 1 gives us minus 1, all of which equals 0. Alright, so then we're going to try factoring this. So 2 sine theta and sine theta, 1s and 1s. Let's see, I need the 2 to be positive and the other one to be negative. Okay. And setting each equal to 0 and solve, I should get sine theta is equal to a half and sine theta equals negative 1. Well, where do I find a positive sign? Sine is positive in the first and the second. And sine is negative 1 down here at 3 pi halves. So putting this all together, I get pi 6, 5 pi 6, and 3 pi halves. And there we go.